Hello students, and welcome to section 5-4, Transformations of Piecewise Defined Functions. And as we take a look here, we will be looking at very similar functions to what we saw back in section 5-2, but apply obviously the transformation concept to these. Example 1, translate step functions. So Uptown Sandwich Shop is increasing the number of bonus points by 2 in the shop's rewards program. How will the total points awarded for a $3.80 item change? So they show here off to the right, Uptown Sandwich Shop rewards program. 1 point for each $1 you spend, plus 5 points for each visit, and no fractional points are awarded. So when we start off, we'll take a look. It says you can represent the two versions of the reward program with step functions. Use the int function on a graphing calculator to graph the two functions. Okay, so step functions are a version of piecewise functions that we're going to be taking a closer look at here today. And I will ask that you use a calculator, of course, to go through the process here. And the reason is because it does ask you to use this int function, which stands for greatest integer function. Okay. As we continue, we'll go ahead and take a look. Starts off here, as you can see, with reward points equal to the dollar part of the amount spent plus the bonus points. This is a kind of generic setup for us to formulate our plan here. As we continue, before f of x, and that will be equal to int, so the greatest integer function, and then x, that's what we're going to input into the calculator, plus 5. Well, after g of x, the second function, is equal to int, so greatest integer of x, plus 7. Now, as you can see below, of course, or off to the right and below here in a moment, well, off to the right it does say an increase of 2 points. So we go from bonus points of 5 to bonus points of 7. Again, increasing the number of bonus points by 2 is what we're looking at doing. So as we continue, it does ask you to enter in the functions, okay, and then graph the functions. So this is where we're going to go ahead and take a look at the graphing calculator. And I may also use Desmos just to kind of give some folks an extra option. Okay, so let's take a look. I will be using Desmos, and in fact, on each respective function here, when we use Desmos, we'll be able to see very nicely how each function compares and also the progression as such. So we have, like I said, f of x equals the greatest integer x plus 5. And g of x equals the greatest integer x plus 7. So if we take a look, and I'll go ahead and get Desmos opened here as well, what you're going to go ahead and do is for the first function, you're going to go ahead and type in the function in blue. Now it may not be blue on Desmos, but still we know it's going to correlate to the blue function there in the notes, so that when you hit the keypad, show keypad, you're going to click on functions. And interestingly, the function we're going to be using under miscellaneous is floor. And if you hit floor and then x, you'll see this what we call step function. It's a version of a piecewise function that we have discussed in the past. Obviously, piecewise functions are parts of either lines or functions in general. In this case, we have multiple segments. To that, I'll go ahead and add 5. So there you have it. There's your first piecewise function represented as such, the f of x graph. The other function, of course, g of x, we'll go ahead and hit floor, and then again x, and we will add 7. Okay, so side by side, or one on top of the other, we can see these two piecewise defined functions take shape, again also referred to as step functions. So each step in particular, you can kind of see here, for example, 0, 5 on one graph, and on the other, let's say, we've got 0, 7. In the context of the situation, again, we talked earlier as to how The greatest integer function for, again, all intents and purposes for the blue function, dollar part of amount spent in blue, INT(x), so that's what 0 would represent, greatest integer for x at 0, x being 0, and then the reward points, f of x, would be your output, or your, in this case, dollar amount, or sorry, points, in fact, 5. Those are the bonus points, particularly. The dollar amount, again, is the x value. So as those continue or progress, other points, for example, you've got 1 comma 6, technically is the second step, but if you just go a hair shy, you'll see 0.98 comma 5. Once I scroll to the right, though, it jumps. So get closer and closer, look at that, it jumps to 1 comma 6. So we're now at the second piece. Similarly, if I go to the other function, get closer and closer to 1, I'm still at 7 for my y value, but as I approach, boom, it jumps up once you reach 1. So in a sense, it's kind of like, as we saw with piecewise defined function, in a sense, it's kind of like looking at an open circle. So there's an open circle at 1 comma 7 on the green function, and there's a closed circle at 1 comma 8 on the green function, one step above. So let's take a look. That's, again, how Desmos is going to play things out for you or help you see things. I'm going to go ahead and take a look in continuation, but using the graphing calculator technically, as they describe. So your graphing calculator, if and when you have one, you'll be able to type it in as the INT, or greatest integer, of x, and then +5 for one function, +7 for the other. As you can see, the graph takes shape accordingly. At x equals 3.8, and I'll bounce back to Desmos, the value of y increases from 8 to 10. And you can see that in the graph. It also describes, as you can see just below, that the graph is translated up 2 units. The points for $3 for a $3.80 item increase from 8 to 10, from one graph to the other. You'll see that. Now I do want to go back and kind of highlight that idea when x is equal to 3.8. Technically the graph should be just the first quadrant representation. So let's go to 3.8, which is here-ish. There we go. So at 3.8, you're at 10 on the green graph, and at 3.8, you're at 8 on the blue graph. Again, the blue step, which is horizontal, has a y value of 8 on, and at that point. And then on the green, like we saw, it's at 10. So 3.8 comma 8 and 3.8 comma 10. All of those values, if you think about it, should be 10 because the segment is horizontal. It's not until you get to this open circle right there-ish at 4 comma 10 technically. At 4 comma 10 it's open, and at 4 comma 11 on the next step up it's closed. Okay. All right. So let's move on. Now, I am going to stick to Desmos because, as we've already discussed in the past, most students don't have a graphing calculator quite yet. So Desmos will be your go-to. All right, as we continue, example 2, vertical translations of the absolute value function. How does adding a constant to the output affect the graph of this absolute value? Okay, so we have discussed absolute value functions and their graphs. What are we going to see though when we add a number, a constant to it? Compare the graphs of h of x, which is the absolute value of x minus 4, and g of x, which is the absolute value of x plus 2, with the graph of f of x equals the absolute value of x. I will again use Desmos, so I'll pull that in here, and we'll make an observation as such. I do want to make sure though that we type in, to kind of kickstart this process, make sure we type in the parent function, and everything from there will compare accordingly. So we see we have absolute value of x and absolute value of x minus 4, and then here we just kind of maybe jump right in and start looking at the differences between the two. So the purple graph is the parent function, while the black is the transformed graph. So I would argue very obviously that the purple and the black compare by you shifting down 4 units. Every single point shifts down 4 from purple to black. Similarly, if we were to type in the other graph, of which is going to be again an absolute value. Okay, so we'll see here the absolute value of x, and then plus 2, and that of course is depicted in red there, wherein you're seeing the shift, I would argue pretty obviously, up 2. So from purple to red, you're moving every point up 2 units. So that's a nice quick way to depict it on Desmos. Let's take another look though, as they describe in their graphs. They'll do the same thing. They have the same axis of symmetry actually, all three graphs. Their vertices are different, of course. The parent function is at 0, 0 for its vertex, while shifting it down 4 has a vertex now of 0, negative 4. Again, axis of symmetry cuts it in half such that x equals 0 is that line of symmetry. On the other graph, of course, the red now from the blue, from 0, 2 up 2 units to 0, 0, pardon, up 2 units to 0, 2 highlights that shift. Again, the axis of symmetry is identical. Adding a constant k outside of the absolute value bars changes the value of f of x or the output. It does not change the input. Okay, I don't think that's a big surprise, again, just by virtue of looking at the graph. The value of k in g of x equals absolute value of x plus k translates the graph of f of x equals absolute value of x vertically by k units. The axis of symmetry, again, does not change. So we're shifting it up and down. That's the idea. Example 3, horizontal translations of an absolute value graph. So what we're going to be taking a look at here, again, in comparison of a function g to a function f, f being the obvious parent function again. We'll go ahead and maybe just go right into the idea without maybe using Desmos, because they show it nicely here, such that you can see the blue function as the parent. They highlight the typical depiction of which you've got a vertex of 0, 0. 2 other points if you wanted. You probably should by hand, if you didn't use your calculator, of course, at least 2 more, so that your V shape takes shape. The vertex of this function ends up being 4, 0. Okay, and you could plug in 4 to prove that out. You could also plug in another point here as well as here to prove that out. So we're actually seeing from blue to red that you're shifting the graph right 4 units. Everything shifts, even the vertex as well as the axis of symmetry. The axis of symmetry now in that red function is x equals 4. Adding a constant h inside the absolute value bars changes the value of x, the input, as well as the value of f of x, the output. The value of h in g of x is equal to the absolute value of x minus h. It translates the graph of the function horizontally by h units. And if h is greater than 0, it's shifted to the right, and if it's less than 0, it's shifted to the left. And the translation, of course, is that. Because the input is changed, the translation is horizontal, and the axis of symmetry also shifts. One thing to be very careful with regards to this particular quantity, if x minus 4 versus, let's say, x plus 5, or x plus 4 for that matter, the minus sign should be indicative, even though we're seeing here it as a minus, indicative of this h quantity being positive. So it's x minus positive h, and that's going to be a shift to the right. Here, the way you want to think of it in terms of a rewritten version, and I do recommend you write this down, the rewritten version would take shape as such: x minus negative 5. So x minus a negative, of course, is still a positive. It's plus a positive. Your h value, because it's negative, would be a shift to the left. So be careful with the sign analysis on those. X plus 5 would be to the left, while x minus 5 would be to the right. Similarly, part A there would be shifted to the right 3. So be careful. Use the calculator to help you in that particular analysis. I will ask that you try example 4 on your own, as well as example 5. We will come together at a later time to finish up the rest of the notes, but also touch base on these remaining examples, example 4 and 5. But try those out on your own and check against the completed version of the notes. Measure yourself against those.